all the things here. Okay. Alrighty. So first of all, let's start our class. I have to apologize for everyone because I'm not able to go back to town. Currently, I'm in South Carolina and at my home now here because my wife's here and we have children and she is not at home, so I had to take care of the children. I cannot leave the two children at home, by themselves. So they're not in age to be independent yet, right? So great. So here, but however, I'm able to going back on Friday though, and so on Fridays, and we will have a lab as normal, so like yeah, it's kind of like it's kind of like a pretty hurry, like pretty long drive. Alrighty, before class start, anyone have questions? All right, just small thing here. So one thing here is what we'll do is today we go to chapter 4, right? And a small announcement here is we do have this like project 1 and both project 1 homework 3 due this Friday. It should be due about last week Friday as well as this like coming Monday. However, I think some groups still not quite finalized yet. Probably rushing for them to just submit on the rush because the project it definitely take into probably a little percentage here. We want to make sure everyone the grade is not suffering just because rushing. So we want to make sure everyone is successful throughout class. Because this is the reason, we just give you guys a little time, and so make Friday. So if you do have questions, if still somewhere confused for like a project or class project, right? So please ask me on Friday or lab session, so I can I can like help you on the way, right? Just be noted because I'll drive back on Thursday, but tomorrow it's a little bit like probably a bit tired. Hopefully, I'm not too tired. But usually I'm pretty energetic person. I'm not sure my talent is, and I have to drive back. Yeah, Nick coming here. I have to drive back to South Carolina on Saturday because I have to drive here to a class on Thursday. Uh, Taking my children to to a town here, and I drive back to send them back. But I thought to drive like yesterday, but they then they're not are not able to drive, and so my child doesn't feel good, and they cannot take like 8 hours 8 hour trip. So I think they feel it better today and feel probably even better tomorrow. So I can put them on road. So drive there, take about 8 hours so. So I come back. I have to drive there Thursday. I go there, take our class, finish our lab, and send them back on Friday night. So there's a plan, but I will drive back. All right, I'll drive back on Fridays to have a lab here. Okay. So let's go back to topic. The topic here is chapter 4. So chapter 4, I think is interesting chapters. So let's start our chapter. I believe most students should be here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So I think we have I think half our class online here, okay? But we do have lecture recorded. If in case someone missing the lecture, they can watch the videos. All right. So here, chapter 4 is the diode here, diode. So the diode is very interesting one. It has been heavily used in the industry through everywhere. So let me share my screen here, okay? All right. So let's go through the and here. Let me move this one here. All right. So let's make this presentation mode. So I this semester actually did a little bit different things. This semester is I try to make a summary for each chapter. My hopefulness here is you just read this summary, you can get the majority of the chapter, at least a particular slide. So for part 1 here is I made only 2 slides here. You see, very simple. So diode is here. Diode is looks like a simple thing, right? And we already started chapter 3. Diode is nothing more than an NP junction. Because NP junction, right, it has called semiconductor. What do you mean by semiconductor is on the reverse bias region. So reverse bias region, it is it is like called reverse biased, right? Reverse biased. This is like forward region, so forward biased. So it yield this thing very famous called IV curve. IV curve means the voltage is x-axis, the current is y-axis. So in forward region, so the current jumping very quickly. However, in reverse bias region, the current is just stopping here immediately. So between here to here, there's no voltage. Sorry, there's no current. But after passing here, we start to have this current ongoing, right? So as we already, Nathan coming, as we noted in the chapter 3, so from this region here up to here, we call it called breakdown region. Breakdown region and avalanche region, okay? Breakdown region means that they start conducting some current, right? But avalanche region is conducting a lot of current. Typically speaking, like chapter 3 indicated, typically speaking here is this breakdown region here, there's not much damage for. However, in avalanche region is very damageful. So we have coming second test, right? If I ask this question, you should know this, okay? And before breakdown region, right, we call this thing is just no current here, right? So however, even in the breakdown region, the voltage is still very limited here. See, the voltage almost constant here, almost constant. So what I mean is, even in reverse bias region, the current can increase very quickly. However, the voltage doesn't change much. Same thing as the forward region here as well. You see, the current in forward region change very quickly. However, the voltage is not changing. Look, the voltage is just almost constant. Here we said it's called threshold voltage or NP junction voltage. Do you remember how much voltage is? If you don't mind, you can test the answer in the your chat sections. You're welcome to test give this answer in your test sections, okay? Right, you put it in chat, okay? Right, is anyone put in chat sections here? Right, let me see where's the chat section. Yeah, very good. Look. Yeah, thank you, Matthew. Look, haha, you are the winners, guy. You guys are winner. Okay, all right, good. Let's put here, right? Chat sessions is very important. Back to the COVID-19 time, I taught mostly just like problem, especially first year, and 99% online. That time I taught at VMI, Virginia Military Institute. I taught mostly cadets. we have fun time, and because I'm pretty like a funny person, I'm pretty cheerful, and cadets, sometimes tired. I cheer them up. I just funny story, right? And then to not make you sleep. Hopefully, no one sleep here, okay? Right, but back to VMI time, right? So cadets are so tired because they're running around every day, right? So back in the class time, right? So the cadets used to fall asleep. They literally fall asleep in class. Why? Because they just finished running probably half marathon and came back to have class. And of course, if I was them tired, so actually I just like walk around my daily task. Just while I have class, I just walk around, have fun with cadets. Just like right? And high five with them, right? High five and tap on the shoulders. I'm not crazy yet. Some professor in VMI, because they even ask cadets lifting their foot up, so cadets not fall asleep. All right, just a little funny story. Hopefully engage you here. Okay. All righty. So let's go back to topic here. Okay. So we remember this one here, right? This is review mostly chapter 3, okay? All right, thank you, Luke, and thank you, Matthew, again, okay? So chapter 3 will talk about IV curve, right? We talk about breakdown region, we talk about avalanche region, and we'll talk reverse bias, forward bias. So now is come to the equations. Hopefully you still remember the equations. Probably you do, right? Because you probably work on homework 3. You are finished. I know someone already finished. They already submitted. So here is this one called IV curve equation. Extremely important equation. Extremely important equation. So this equation says this RS called, what is RS name? All right, Nathan, come back again. What RS here again? Yeah, please type in the chat box. What's RS again here? What's the name? What's the name here? RS? Anyone know? Anyone know the RS here? Oh, drip current, Zach. Thank you. Right, drip current, right? Drip current. Thank you. Thank you, right? Thank you. We were close. Anyone else want to volunteer? If you don't type, you sleep. Don't fall asleep. Don't fall asleep. You're probably okay in morning time, right? Anyone want to try it? Yeah, Matthew again. All right, Matthew. Thank you again. Awesome, guys. Thank you. Current source. All right, current source, right? Yeah, that makes sense, right? Current source, right? Yes. Yeah, if I were you, I would make same guess here, okay? Make same guess. Anyone want to try it a bit? Alex? Alex want to try it a bit? No? No one try no one try anymore? Yeah. Right. Alrighty. No one try anyone want to try it? Thank you, appreciate it. This thing called saturation current. S stands for saturation. I mean, here saturation current is actually this thing. Saturation current is similar to drip current, and it's very small number, by the way, very small number, right? And yeah, thank you, appreciate it. Thank you, Matthew. That's fine. That's definitely fine. So, but for coming test 2, right? I want to Everyone just study this stuff, okay? Saturation current here is, means it's little current, right? Very little. So it's 10 raised to -16 or -18, which is the common magnitude. So saturation current, the equation is A multiplied Q multiplied Ni square multiplied bracket dP, this stuff here, okay? dN, right? Alrighty, one more time. Just recall chapter 3, right? A is cross-section area, NP junction cross-section area. Q is magnetic electron charge, which is 1.6 multiply 10 of 19, right? 10 raised to 19, minus 19, by the way. And Ni square is multiplication free electrons and holes, right? And Ni is typically 1.5 multiply 10 raised to 10, okay? Which is silicon, right? Constant. Of course, different semiconductor will have different constant here, okay? Steve, come here. Thank you, Steve. So there's a bracket here, the dP and divided by LP, right? dP is diffusion constant, right? Diffusion constant in the P junction here, right? In the P section, right? And this dN diffusion constant in section here. LP is your length in P section. Ln is length, right? In the diffusion length N region, diffusion length P region. Nd means the electrons, right? The number of electrons. Na is number of holes. Even based on equation, you can say, oh, look, electron move around here, the holes move around here, and together the formula is called saturation current. Saturation current, okay? And in proportion to the cross-section area, okay? Also proportional to the multitude of multiplication of free electron holes. Right, yeah, so this is called saturation current, very small though. And also note here, V is negative. V is negative for this negative reverse bias region. V is a positive for the forward bias region. Therefore, you can see, right, if V is positive here, you can obviously, well, during forward bias, the current is increasing very quickly because, see, it expands exponentially quickly. However, in reverse bias region, you put the V is negative here, then reduce exponentially. Right? Either increase exponentially or reduce exponentially, depends on the sign of V here, right? Sometimes people don't use the -1 here, okay? This -1 because it's so small, right? Because Rs is very small number, right? Rs is so small number, and therefore some people get -1 cancel out. They not cancel out, just ignore it. Just ignore it. So the equation becomes I equal to Rs multiply E raised to V divided by Vt. Divide. This is not N, right? Divide by V divided by Vt. V divided by Vt. So the Vt here is called thermal voltage. Again, the magnitude of the thermal voltage here is 25.3 millivolts, right? Some people use 25.9. Some people use 25. And I think for this, we just use 25.3 millivolts, which is a constant number corresponding to only room temperature. Room temperature in electronics, we refer to 300 K. If anywhere tells you, okay, room temperature, you say, oh, 300 K. Right, 300 K, okay, 300 K. Right, and often in the equation wise, we use K, okay? We don't use Celsius, okay? 300 K is, you convert to Celsius, is 28. Who want to volunteer? Who want to volunteer to Google search? 300 K is how much temperature? I believe it's 26.8 or 28.6, either way. Who want to volunteer? Convert to 300 K to Celsius. Anyone want to volunteer? Convert to 300K to Celsius? All right. You can speak. Oh, yeah, Alex. Awesome. Yeah. See? My second number is right. It's not 28, 26. 26.85. Thank you. I appreciate it. Thank you. Thank you, Alex. All right. You guys are awesome. All righty. So this is a brief review here, and this review also crucial. If you don't quite understand this one, you'll be lost for a lot of equations. So this one hopefully give you some foundation. All right. Now let's go to this little more complex equation. All right. So this, if you understand these two slides, you are in good shape in chapter 2, okay? In chapter 4, okay? Part 1, okay? So I condensed all the slides, important stuff, or we call difficult stuff, to the two slides here, okay? All right, this slide a little bit difficult. I mean, it's not too difficult, all right? You given this curve here, you get 2 points. The 2 point here called I1, I2, right? You see, there's no -1 here, right? No -1. Why? Because we skip it. Why? Because why we can skip it? Because saturation current is so small. It's teeny tiny number. Is like a 1.6 multiply 10 over -18 or negative 16 or negative 15. That's a it's a small number, extremely small. It's just zero, literally zero. Okay, of course. If a billion transistors, it's not zero anymore. Okay, but it's small. Okay, the RS is close to zero. Therefore, we can ignore it. You say, oh, RS is so zero. I mean, does this still make sense? Because it's so close to zero, you multiply makes sense. Yes, indeed. You can do the math. Why? Look. If V2 or V1 is 0.7 volt, remember, VT is 25.3 millivolts. VT is 25.3 millivolts. Anywhere this thing is 0 volt, 0.7 volt, or 1 volt. You know, I mean, depend on semiconductor. Some diode is most silicon diode. You know, the threshold voltage is 0.7. Okay, because it's constant, almost constant. Look, almost constant. But it's not every diode born equal. I mean, this diode is all different kind. So they have like a germanium diode there, right? They have silicon diode there, right? And they have many different kind of weird IGBT, you know, those like can also diode here. IGBT, right? Is used in electrical vehicle here, right? And I will wish all this diode like equally stuff, but they're not. They all different kind, all different kind. I just tell that Dow John told me diode is threshold voltage, or fire this threshold voltage here is just like a 0.7 volt. I just apply 0.7 volt everywhere. Until one day, like after graduation for 10 years later, you work on this like let's say engineer electrical vehicle or like electrical car or something. I grab a dial and say, oh, look at this shit. That's untrue. That's not true. The threshold voltage is not 0.7 volt, or actually 4 volts. What's going on? Yes, that's because that's the nature of diode. That's the nature of diode. I mean, right. So here is the different manufacturers, okay? Different materials. Alrighty. You pick 2 points here, right? Remember, again, just know this equation here, right? I1 right here, I2 there, right? You divide two equation, right? You divide I2 by I1 here. You got this equation. Then both sides you got natural log, right? In natural log left side, natural log right side, you can form this V2 minus V1 equal to Vt multiplied natural log I2 divided by I1. All right. Again, one more time. What's the number Vt? One volunteer. What's the value of Vt? Who want to volunteer? Who want to volunteer? What's the value of Vt again? We call thermal voltage, right? What's the value? What's the typical value of the thermal voltage here? What's the value of thermal voltage? All right, Jack. Thank you. Appreciate that. Awesome. 25.3 millivolts. Thank you. All right. Thank you. Appreciate that. Okay. Right. I2 divided 1, V2 minus V1 here. Okay. Here. Let's look at the equation. Someone probably not quite understand the equation here. Okay. Let me how much time we have here. Okay. Let me see. We have 46. We have a little bit time here. Okay. All right. So here is, right. So here is V2 minus V1 is proportional this natural log, right? Relationship here, okay? Alrighty, so this is one equation, right? This is a little bit difficult. Not too difficult, just I2 divided I1, right? And then plug to here, right? Plug into here. And divide them and do natural log, both sides. We got this one here. This is a very important equation. Some questions you cannot solve it. Think about this equation here, okay? The third equation I want to show you, right? The third equation, this equation. So we know that I equals Is multiply E V divided by T, right? Again, this is approximate. Why approximate? Because we ignore the -1 here. So you do natural log on both sides here, right? Natural log on both sides. So V equal to Vt multiply natural log. Again, natural log here, natural log. I divided by Rs. Look. So let's see, right? Now we can do some calculations. If I gave you the I give you anywhere a current on the equation here, on the curve here, any current. Let's say I give you diode. I tell you that this forward bias current I ask you their voltage. Yeah, you can calculate. Why? You can plug in the Vt here, multiply natural log I to Rs, right? Or I can give you probably V1 here. I give you I2, right? I mean, I give you I1. You can calculate V2. Or I give you V2. I give you I2, I1. You calculate V1, right? You see? These three equations can do lots of calculations. Alrighty, and let's quickly wrap up. So what I do here is let's go back to a lecture here. So lectures, let's look at this chapter 4 exercise. So chapter 4 exercise here, question number 2. So here is, let's look at this question, okay? It's given a silicon diode, right? And this is 1 milliamp device. Displays a forward voltage 0.7 volt at current 1 milliamp. Evaluate the junction scaling constant Rs. What scaling constant would apply for 1 amp diode? Right. And here, by the way, they call scaling constant here, right? Scaling constant. And this scaling constant is purely mathematical. Means scaling constant is almost a constant here. Actually, we call saturation current. That's a more physical term, okay? The scaling constant more like a mathematical term, okay? Don't get confused. So here is the tell you 1 milliamp device, okay? So typically the 1 milliamp anytime we say 1 milliamp diode, we call small signal diode. Small signal diode. So at the forward bias, the threshold voltage is 0.7, right? And so it gave you the I here. It gave you the voltage here. It asks you to calculate the Rs. All right. So which equation to apply? So gave you this voltage here, 0.7, right? It gave you this current here, right? It asks you to calculate Rs. You probably which equation we can use? So you can use this equation, right? We give the voltage here. We know thermal voltage. We know current, which is 1 milliamp. We can calculate Rs, right? Rs, right? Let's look at the answer here. The answer here, right? So we know that I equal to Rs multiply E divided by T, right? So the situation here is Rs is I divided by E divided by V divided by T here, right? So that I is 1 milliamp here, right? V is how much V here? How much V there? Right. How much V there? How much this V here? How much this V here? Yeah, we said here, right? 700 millivolts. Right? Divided by T here, right? With 25, right? You can 25, 25.3. I would say, you know, I mean, you can use 25.3, 25, both is okay, right? I mean, yeah, thank you. All right, perfect, perfect. So here is, and what I here? I is 1 million, right? Oh yeah, 1 million. Sorry, Zach. Thank you, but thank you, Zach. Though. Thank you, appreciate. It's 1 million, right? 1 million. Okay. So you calculate RS, right? RS. There, see that? RS. RS is calculation, part equation there. You got look. This so teeny tiny number. Okay. Right. Also, the second part equation asks you if change I, right? I to not 1 million anymore, right? We change to 1 I. Then right, and is RS still same, not same, right? Probably not same, right? Let's see. If the current is not 1 million, not 1 million anymore, right? Rather it become 1 an, right? Let's look. So now is this is not 1 million, right? 1 an, right? 1 million is about like 1,000 times, right? Right, 1,000 times. If this is 1,000 times, and therefore it become 6.9 10 of negative 13. Because this in before for 1 million the current correspondingly is negative 16 here, right? For 1 amp is proportional, right? Because this is 1 amp here, right? Is 1,000 times, right? And even 1,000 times the saturation current is just so small number, okay? It's so small number. Alrighty, so everyone got the idea here? Anyone questions? This is how we apply the equation right in place. Right in place. All right. So now let's move forward, okay? So we finished this two most important thing for class. So right, I believe our class finished like 11 or let me see, 11 what? Our class finish time 11:15, right? 11:05, 11:15.
Yeah, that's about 20 minutes from now.
11 what?
11:15.
11:15, right? Yeah, we have a little time. We have 11:15. We have, yeah, we have 55 minutes. We have, let me, how many minutes we have here? Let's second, let's check. We have 11:15. We have about 20 minutes. Thank you. Yeah. Great. We still can cover a lot of stuff here. Okay. All right. Thank you. Right. Thank you. 11:15. Like 20 minutes. All right. So we've actually finished pretty much this part one. But I do want to show you some interesting things, also important. Although you say, look, Dow Jones finished part one, right? I mean, is that all thing I have to study? Probably not. You probably start a little beyond this, right? Because these two slides show you pretty much the most important. Alrighty, now let's look at the diode features. We are talking about reverse bias, forward bias, right? Reverse bias, there's no current. Forward bias, of course, out breakdowns to current, right? But this ideal diode, ideal diode means different from real diode. Ideal diode, it means the reverse bias, the belief is, there's no current there, there's no current. Which is not true, by the way, okay? For real diode, right? So, however, for forward bias here is, there's a lot of current. So they believe is forward bias and rather than 0.7 volt is 0 volt. Is it really? That doesn't make sense. How come? Why 0 volt? There's a lot of current. Again, this is called ideal diode. Ideal diode. Ideal diode. It's almost equally speaking to our like op amp. Remember? So the typical equation we applied called infinite open loop gain, right? Which only refer to ideal op-amp. For real op-amp, however, yes, questions. All right, yeah, Zach. For non-ideal, how much current actually leak from the cathode to the I see. Zach asked very good question. For non-ideal diode, right? For non-ideal diode, look, this is non-ideal diode. The real diode, look. There, but you think about 0.7 volt, and only type of 0.7. It's you cannot connect current through zero voltage. You only can connect current, however, about 0.7 volt. Right? Actually, it's almost starting get a little bit current. Little bit current called cut-in voltage. We call cut. Let me see. Called cut-in. Like 0. Like 0.5 volt. At this time, you already start to call not to look. Sorry. To everyone. Let me see. Right. So this Zach asked a very interesting and fundamental question. So what I mean for non-ideal diode here is about 0.3, 0.5 volt. You already can see the current. It doesn't have to wait for 0.7. Look, this already started to have something there, right? But only about 0.7 start to increasing so quickly, right? So as far as how much current is start to conducting about 0.3 volts, very little bit, not much. Typically million volts, like 1 million, 2 million, 5 million, like 10 million. Okay, very little current. Okay. Thank you, Zach. Very good question. All right. Again, for ideal diode, however, we say, look, on 0 volt, we already got a lot of current. Okay. And if you reverse bias, there's absolutely no current, which is not true. Okay. And the reverse this thing like NP junction here, they call cathode here, they call cathode anode. Okay. Right. We can skip a little bit, right? Yes. Right. Ideal diode, right? All right. Look, small equation here, right? Simple one. Right. So ideal diode, right? Look. If I say this ideal diode, if let's say and if I give you this diagram here, I tell you this ideal diode, I ask you to calculate this current, you have to be careful. Okay, you have to be careful. Look, if this ideal diode, right? If the ideal diode and the voltage drop, not 0.7 volt, okay, rather 0 volt. Make sense to you? So if the ideal diode, you give this scenario here, and this one is just like and this one is 10 volts divided by 1K here, right? We got 10 million, okay? Because the no voltage drop. Okay? So on this one here, because this thing reverse bias, forward bias. Tell me. This one here, reverse bias, forward bias. Who want to volunteer? Reverse bias or forward bias? All right, thank you, Luke. Appreciate that. Yeah, great, thank you. Yeah, right. Yeah, LTM 2M. Thank you as well. Right. And is Logan? I don't know. I need to check. Sorry, I cannot recognize the email. Okay.
Right. Yeah, it's Logan.
Oh yeah, see, good guess. I'm too smart. All right, just to make you cheerful, guys. Okay. Right, don't fall asleep. Okay. All right. So look, this one here is right. Yeah. Look, right. So this one here is reverse biased. Again, for non-ideal diode, is because even in reverse biased, if breakdown region, there's a lot of current, remember? But we talk about ideal diode. Okay, talk about ideal diode. For ideal diode, reverse bias is just like an open circuit. Open circuit. Because open circuit, there's no current. The current therefore is 0 milliamp, 0 milliamp, 0 milliamp, okay? And the voltage here is 10 volt because look, 10 volt. Why 10 volt? Because open circuit. Okay, open circuit. All right. If I give the simple question, anywhere like anywhere you should be able to calculate. Okay, thank you. All right, let's go move a little bit forward quickly here. All right, a little concept here. Okay, look, this input waveform. Okay, one big application for diode is used as regulator, called voltage regulator. Okay, or voltage rectifier. Okay, you will all work on senior design, right? Because you work on senior design, I believe you use like voltage regulator, voltage rectifier. You probably not use voltage rectifier too much, but most group at least use like let's say 20 volts to 5 volts, right? All right, or 12 volts to 5 volts or 3 volts. So you can use Arduino stuff, right? So those stuff actually use a lot of diode. One big application for diode is use rectifier. For example, this is a given input waveform. Out only one diode. Look, what do you get? What do you get? You get pretty much only the half wave. See that, right? That's called half wave rectifier. So that means only half wave got left. We name it half wave rectifier. Right? Yeah. Error one. Okay, error one. Yeah, we're recording the screen. You can halfway rectifier. Right? This chat box just like look. Look, you are good shape, right? Look, right? Right. Alrighty. Awesome. So what we do here is so the question is how come we got a halfway rectifier here? Let's do a little bit like analysis here. Look, in 4 bars here, right? Let's say if the waveform here, this become negative. If this negative, right? If this negative is still any this thing 4 bars reverse biased. Volunteer. If this negative waveform here negative, this thing 4 bias reverse biased.
It's reverse bias, right?
Yeah, thank you. Right, thank you, Matthew. Right, appreciate that. Thank you. Yeah. So because reverse biased, there's no like nothing much, right? Nothing much. Reverse bias the open circuit. So reverse bias here, right? Reverse bias here, right? Just open circuit here, right? Because open circuit is open here, there's 0 volt. Error 0, right? Error 0. Look. 0. Make sense to you? Great. So even 4 bytes, however, like this one here, right? Look, this one here, this region here. So if this region here, this positive here, right? Positive. If the thing positive waveform, and this thing negative, this is ground here, right? Ground. Positive ground. This now become in this region, we call it the region. What's the region here? One more time. This region. One volunteer. Anyone want to volunteer? Thank you. Appreciate Zach. Alrighty, 4 bias region. Thank you. Appreciate that. Yes. Reverse bias region, 4 bias region. Reverse bias region, 4 bias region. Reverse bias region. Therefore, we got 0, there. All right. Thing to note. In the 4 bias region, we assume there's no voltage drop. Therefore, output voltage is still VP. However, this is not true for real diode. For real diode here, is voltage drop, no voltage drop? If it is, tell me how much voltage drop.
Possibly be 0.7.
Yeah, Matthew, what's your number?
I said it couldn't possibly be 0.7, could it?
Yes, that's absolutely right. That's absolutely right. Yes, I mean, of course, that's typical diode. Okay, for special diode, a different story here. Okay, but really it is 0.7 volt. So here, if I tell you this ideal diode, when you draw the stuff, let's say test 2 here, right? When you draw this diode and this off voltage is VP, okay? However, if I tell you this non-ideal diode, the VP is still VP or not VP anymore here? Still VP or not VP anymore?
It's still VP.
For non-ideal diode, VP or not VP? Logan said no. Yes, I agree. But what's how much? How much? It's not VP, but how much? Yes, thank you. Because there's voltage drop there, okay? The voltage drop, the 0.7 volt drop here. Voltage divider, right? Voltage divider, okay? Right, all the voltage here is equally shared by VO and VD here, right? Not equally, sorry, share, right? Unequally shared. All right, thank you. Alrighty, so this is important, called halfway rectifier, okay? Right, another interesting thing here, okay? This thing, the second applications. This diode, right? Simple application. This is called protection circuit. Right. So this one here, protection circuit is, we want to say this thing here. Look. Given you have this, let's say this is your phone here, okay? All right, your phone. So your phone only can, let's say, not mostly smartphone, right? But let's say your phone is not smartphone. Only the charging voltage, let's say the charging voltage, let's say 5 volts, okay? And you probably plug into different kind of like a socket. Sometimes you plug in, you're on the wrong, you accidentally plug in, let's say 15 volts. All right, let's say we are 15 volts, but we all will desire 5 volts. Let's say you charge your phone, right? You don't want to like damage your phone, right? So you want this thing as 5 volts output. You don't want like 15 volts, which is bad. In this case here, we want to make sure is we able to protect the phone here. So what do? We simply put a voltage source here, 5 volts voltage source as well as diode. That's all we do. Actually, you can do yourself, and you probably can like you have charger somewhere and you want to make this constant voltage output, and you connect diode and plus voltage source. That's all you do. And you say, really? Yes, it is. I tell you why. So, I mean, let's see. If we add smaller 5 volts here, right? Let's say 3 volts. You here 3 volts. Here 3 volts here, right? And here 5 volts. And this thing become conductive, not conductive. 5 volts here. 3 volts here. This 4 bias reverse bias. 5 volts here, 3 volts here. Again, I ask you the diode 4 bias reverse biased.
That'd be reverse bias, right? That'd be reverse bias because the
yes, thank you, Matthew. Right, it's reverse bias because reverse bias here is this one should be open and close.
Open.
Open. Yes. Yes. Thank you. Look, if it open here and all the current flying through here, right? Right. So VO equal to VI. Right. VO equal to VI. Right. Whatever VO you need equal from VI. Right. However, if VI keep increasing here, become dangerous. Let's say your phone anywhere below to 5 volts here, that's fine, okay? And so you don't damage your phone, right? Let's say 2 volts. You still can charge very slow though, okay? But but definitely not beyond 5 volts. Let's say accidentally plug 10 volts here or 15 volts. 15 volts here and 5 volts here. 4 bias reverse bias. 15 volts here, 5 volts here. 4 bias reverse bias.
Forward biased.
All righty, great. Thank you. I think Logan, right? Logan? Yeah. So here is, then you have this like yeah, right. So I have 15 volts here and 5 volts here, forward bias. If forward bias here, let me see. Oh, if forward bias here, what's VO equal to? If forward bias. For ideal diode, forward bias just almost like a short, right? Almost short here, right? It's a piece of wire here, right? If forward bias is just like a piece of wire, there's no resistance. Either on or off, right? That's ideal diode. If forward bias is just on, right? This becomes short. VO should be equal to what? Who can volunteer? Tell me the answer. Sorry. What's VO if forward bias?
PVT.
Sorry?
PVI.
Ah, really? Aha.
If it's
If this short here, if this short, VO equal to
0.
VO equal to
If it's short, wouldn't it be 0?
ah. See, Matthew said if short is 0 here, VO becomes 0, not 0. Let's see. Give a two piece of wire, right? You connect 9 volts battery. Then you use voltage meter to measure this battery. How much voltage you got? Let's say 9 volts battery here. Or 5 volts battery, either way.
The voltage of the battery.
Huh?
The voltage of the battery.
Yeah, exactly. You give a piece of battery, let's say 9 volts battery here, right? You voltage meter, you measure, that's you would be expecting 5 volts or 9 volts, right? Yes, you're absolutely right. If this is short here, the VO equal to V plus. If VI less than V plus, VI equal to VO. Look. See that? It's curve. If in the test asks you this draw this curve, you should be able to draw, okay? If I change a little bit, hopefully you can still able to draw, okay? All right, let's move, okay? Everyone have questions? Any confusions? Anyone confusion here? All right, looks okay, right? All right. So yeah, that's pretty much there. Okay, so you will go there. So you'll finish here. All right, this one here. This concept wise. So so temperature will increase. Let me see. I don't want to get lit here, right? Oh yeah, we have about 1 minute. So I think we can probably just stick around here. So just one more thing here, right? This saturation current will be increasing every temperature increase, right? So if you increase 5 Celsius, this IS will double. Remember, yes. Any questions? Remember, before I show you, I tell you this like my story, like a car accident. That's saturation current, right? Or drift current. I mean, this again, you know, this saturation current, mostly like due to this, like you know, mostly due to this, like you know, this like a thermal effect. Okay. Yes, so this thermal effect is make a large deal, right? So it's doubled every 5 Celsius increase. You see, this thing is phenomenally large, okay, and if a big temperature. Alrighty, guys. Any other questions before I let you go? Any question for our class project? Homework 2, homework 3? Ah, okay, alrighty. So, yes, Zach, you can stick around. I can help you around here, right? Is okay to you? right? All right. So you're welcome to stick around here. So if you want to, okay. I mean, you don't have to, of course. And so I can help you here, okay? And if you want to leave, however, and you're welcome to go for something you feel pretty busy, okay? Right. Thank you. I appreciate your time. Okay. Thank you. Right. Let's stop recording here. Right. So let me stop recording here.